Hi everybody. Today we are going to see the performance analysis of a actuator through numerical analysis technique. So we are going to use magnet software for this purpose. So open the magnet software installed in your computer. So you get a graphical user interface window. So in this window, the first thing you need to do is go to the default magnet 1 properties and check whether you have all the things incorporated in the properties like units, mesh, solve, adaptation, transient, parameters. Then close the thing. Go to view, open the view window, right click, properties, and view smoothness. You just make this view smoothness as 1 and make this as default. Apply. OK, close. The next one is we are going to model a actuator of length 30 mm and a breadth 10 mm with a stack length of 40 mm. So which is going to carry a number of turns of 100 turns and carrying a current of 2 amperes. Go to tools, choose set units, and here the default length measured here is meters, time in milliseconds, frequency in hertz, temperature in Celsius. So you just drop out this one and choose whatever the units you are going to work with. So for our example, we are interested in working with millimeters. So I choose millimeters, apply, and then close. Then if you want to change anything related with time, frequency, and temperature, you can change using this dropout box like this. Next, go to view, select construction grid. So once if you select the construction grid, automatically it will show the grid both in x direction as well as in y direction. So the length and the breadth of each and every point is 1 mm. So for this, if you want to check, go to line, add line, click this. So you draw from this point to this point, double click, automatically you get a line. If you want to measure what is the length of this line, so go to select construction, slice, lines or arcs, click this and click this line, right click, go to properties. So automatically it will measures 1 and already the unit we chosen is mm, so this is 1 mm. So likewise if you want to measure the length of vertical thing, so you just draw a vertical line, double click, so you get a line. You go to add construction slice, click this, right click, properties, to get 1 mm. So each and every section unit is 1 mm. Right? If you want to delete this line, just highlight this line and delete. Highlight this line, delete. Now we want to model the actuator of length 30 mm and breadth 10 mm with a stack length of 40 mm. So go to add line, so you can draw so 30 mm. So this is 10, so you need to minus 20, right? Suppose if you want to measure this one, so click add construction, right click, properties, 30 mm. So the length is 30 mm. You want to draw a breadth of 10 mm. So minus 10 to 0 becomes 10 mm. And this width is 3 mm. So here it is 3 mm. So once if you make this one, so automatically you get the view of the entire thing. So which is if you want to measure the thing, see, right click, properties, so you get a 30 mm, and this one it is 10 mm, and this one is 3 mm, this one is 7 mm. That's it. So this is a static part. So the next one we have, the next part in the actuator we have is movable part. So that is also in rectangle structure. So that length is same as the stator one, so that is 30 mm, and the breadth is 2 mm. So the air gap between this movable part and stator part is 1 mm. So I just start here with 1 mm air gap. So 2 mm breadth. So here we get an extra line. So how you cut this one? So go to select construction slice, highlight this one, choose the line, then go to segment edges. Once if you segment edges, this line and the extra line will get separated. So if you highlight this, automatically this line will remain different. So you can delete this line. Now you have a static part and you have a movable part, so which is separated by a distance of 1 mm. The next thing is we want to model a winding. So winding is placed in the static part. So the same thing, add line. So you just choose the winding area. So you need to model as a rectangle. The same thing here. So now we modeled actuator with a static part as well as a rotating part. So for electromechanical energy conversion going to take place, we need to model air. So if you want to model air, we need to have a boundary. So we need to draw a boundary over this. So it's an optional dimension in a numerical technique. So you can take any boundary value and make as a box. So inside this you need to model as a arm. Now everything is over. No need to have a construction grid hereafter. So I just remove the construction grid. So this is the actual model, line diagram. Simply we call this as line diagram. We need to make this as a solid diagram, and with the property of material we are going to use in this one. So I am going to use the material of silicon steel in actuator, that is in the movable part and static part and movable part, and a copper in the winding, and in this one this is the air box, air region. So initially I want to model this static part in using material steel, silicon steel. So for that I want to choose select construction surfaces, click inside this one, automatically this area only get highlighted. So go to make component in line, click this to rename this component as static part. So material, you just go to drop out this one. Whatever the material you want to use, you can use. So as far as the example is concerned, I am going to use silicon steel, any transformer steel. So you can use any transformer steel with any gauge. And the distance here, it is the distance is called as stack length. The stack length, as already mentioned, we have 40 mm. select this one, union selected construction type surface, and remove unnecessary vertices on the boundaries. Select this two one and deselect this one, ignore walls, and click OK. So automatically this one becomes a solid piece. If you want to see that, you can go for examine model, choose this, and here you click, just rotate in cross direction, or else you can go for show ZY direction, so that it is easy to understand the model structure. Okay. Similarly, the rotating part, the movable part is also made up of the same steel. So go to construction slice, surfaces, click inside this one, and go to make component in a line, click this, automatically rename this component. This is a movable part. The same material I am going to use, so default that is it is available here. Choose this two, distance the same 40 mm, you click OK. So the next material is I am going to make a winding which is made up of copper. So first side I choose current in and current out. So just the same thing, go to construction slice, click inside this one, go to make component in a line, rename, so winding phase 1. Okay, sorry, go to object. Here what I did is I didn't mention any material, so the material, the previous material used in the movable part is also adapted the winding. Suppose if you want to change the winding, go to the winding phase, right click, go to the properties. Here you have a material, click that material, drop out, so you choose copper, apply, flex. So automatically it is going to be a copper. The next one is again this one, winding phase 2, and go to copper, select construction surface, choose this winding area, make component in a line, so winding phase 2, drop out, change the material to copper, give OK. The last one is the add. So the same thing, go to construction slide, click inside this block. If you see this, see the boundary, whatever the boundary we draw, inside that we need to create the add. So go to make component in a line, click this, so rename that as add, drop out, so you just give material add, and for this particular material add, this ignore walls is useful, so you just select ignore walls and give OK. Now in left hand side, if you see, it is equally matched with your model. The first one is, click here, static part, movable part, winding phase 1, winding phase 2, and add. The next one is, we are going to make this winding phase 1 and phase 2 as a coil. Now this is a separate one, separate component. We are going to make this as a coil. So what I did is, just select winding phase 1, press Ctrl in your laptop or computer, and again press phase 2, go to model, make simple coil. Once if you make simple coil, automatically you get a dot and cross here, and also here you get a coil property. If you click this coil property, now if you see, this coil is one component, single component, whereas this one is separate component, whereas this coil is a single component made up of phase 1 and phase 2. The current in this one dot and cross is current in and current out. Right? Now in this coil, click the coil, right click, choose properties. Here you get a number of turns and current per turn. So as I already mentioned you, the number of turns for this actuator is 100. So you just type 100 and current per turn is 2 amperes. So apply, close. That's it. So if you see this, now the actuator is carrying 100 turns with 2 amperes of current. If you want to examine the model, 3D model, you can examine. See, the 3D model is like this. This is the stack length. So the stack length is 40 mm. So why I said this is 40 mm? Because I mention here the sweep distance as 40 mm. This is 40 mm. So that is 40 mm is common for all the components. See. So 40 mm for stator, and this is a movable part is also 40 mm, winding, everything. So you see. So other phase of the winding. So other phase here, the front phase, back phase. Right? So this is the XY model, 2D model. Now we are going to do the static analysis of this actuator to find what is the force exerted by this movable part towards this static part. So for that, go to solve. You have a solver option, set solver option. Default depends on solver, linear or non-linear. You can choose linear or non-linear depend upon your solver. Maximum Newton iteration. So if you want to optimize through Newton iteration, you can keep on increasing the Newton iterations so that your solution is also get optimized. So source frequency, so your source frequency is 50 Hz. So 50 Hz I give. So you can change this one according to your wish. So if I want to Newton iterations 30 and Newton tolerance as 2, so CG tolerance, you can increase according to your wish. So apply, close. So the next, go for adaptation option. So percentage of elements, this is for meshing option. So you keep on refine your meshing options. If you increase the adaptation percentage, your solution is better compared with the previous one. So this is only for 3D and the H adaptation is for 2D. Then you go for solve, static analysis. Now you get a result window. So in this result window, you get a stored energy, co-energy, force exerted on the static part, winding, phase 1, phase 2 and movable part, flux linkage, ohmic loss, iron loss, current, temperature. So room temperature we specified is 20, so it provides 20 as it is. So here if you see the force exerted on the movable part is 1.71. The torque is 0.0065. The force exerted is 1.71 Newton. And if you want to see that, go to this one, go to the window, choose field of flux function, update flux function. See the flux function, you get what is the flux, maximum flux density available in each and every portion of the movable part as well as static part. See, so you can zoom it. See, so the 0.2646 is here, whereas the maximum force you get is here. The maximum flux density you get is here, the red color. So this is 0.33 Weber per meter square. So what I did is simply I just copied this force 1.71 and put it in a Excel sheet. So this is the air gap for 1 mm. Just go to the view, object, solid model. What I did is, now I want to make for different currents. What I did is, go to properties, instead of 1 amps current, you give 3 amps. Close, automatically it will get 3 amps. Go to solve, static solve. If you see this, see the force now is 3.84. So I just copy down and put it in a Excel sheet. So this is for 2 amps current, this is for 3 amps current, and similarly if I want to go for 4 amps current, so this is the case. This is 4 amps. So this is the air gap is 1 mm, and for different current I get a different value. So if you plot the thing, if current is keep on increasing, your force is also get increased. See, if your current is keep on increasing, your force is also get increased. Similarly, if my air gap get varied from 1 mm to 2 mm for a current of 2 amps, 3 amps, 4 amps, so what will happen to my actuator? So let us see that one. So for that, what you have to do is, first select the air component and delete the thing. Now we want to move this component 1 mm apart from this one, so that the total air gap between this static part and this movable part becomes 2 mm. So what I did is, just I delete this movable component also, but the line diagram stays as it is. Select this movable part, or otherwise choose select construction slice lines and arcs. Now you choose this movable part, go to model, go to draw, then shift edges. So how much you want to shift? You want to shift for 1 mm. So 1, 0. You press OK. So automatically it moves for 1 mm apart. So the distance between these two is 2 mm. Suppose if you want to measure what is the distance between two, just select, add the line, draw a line between these two, then go for select construction slice lines or arcs, choose this one, right click, properties. See, now the distance between these two is 2 mm. Close this one, delete this line. Again you need to make this component, this move aligned as a component as well as air component. So go for select construction slice surfaces, click inside the bar, select make component in a line, rename as a movable part, and select the material as transformer steel. The stack length is same, so you dechoose that ignore holes, click OK. Next, air box, click inside the thing, select construction surface component in a line, rename as air, drop down, choose air, choose ignore holes, OK. So make this as a 4 amps current, so on and on. Now this is 2 mm apart. Let us solve the thing and check what happens to your force? See, the force value is 2.15. Just copy down this thing, 2.15 for a 4 amps current. Suppose if current is going to decrease, what happens? 3 amps current. Solve the model. So 1.21, copy this one, 1.21. So for 2 amps current, solve the model. So this is the difference between 1 mm space between a movable and a static part, and this is 2 mm space between movable part and static part. If you see this, if your actuator is keep on moving outwards your static part, your force is also get decreases. So this is because of to see the flux lines, it is easy to understand. See, the flux density for the previous one is 0.3, whereas it is only 0.25. So the flux density strength is also decreased because of the air gap is more. The strength of the flux is also get decreased. So the force on the movable part is also get decreased. If you see the result and if you plot the graph, it is easy to understand. Separately. So this is the case for 1 mm air gap and 2 mm air gap for a actuator. So if you zoom it and see the maximum value here, it is only 0.25, whereas in the previous one, that is 1 mm air gap, it is 0.33. So that is the difference between a 1 mm air gap and a 2 mm air gap actuator for a different currents, keeping the number of turns constant. So that's all about this session. Thanks for listening.